Module 9, Design, Installation, and Maintenance, where projects win or bleed. This module is where theory finally meets money, schedules, and blame. Up to now, everything we've discussed works on paper. Projects don't fail on paper. They fail in segment design decisions made early, quietly, and often without full electrical thinking. Episode 9.1 is about one of those decisions. Open quote, "How many devices can I really put on this segment? And under what power and safety assumptions?" Close quote. If you get this wrong, no amount of commissioning heroics will save you. Segment design, the question that decides everything. Every digital field network eventually hits the same hard constraint. Power, not protocol, not addressing, not bandwidth, power. And that power constraint looks very different depending on whether the segment is externally powered, bus powered, intrinsically safe. IS, treating these as equivalent is how projects bleed. Powered segments. The network is not the power source. Let's start with the least misunderstood case. In a powered segment, devices have their own power supply. The network carries data only. Power draw does not load the bus. Examples: Ethernet devices, some DeviceNet installations, remote I/O with separate power I. Here, segment limits are driven by protocol limits, timing, traffic, physical layer rules. Power is decoupled from communication. This is why powered networks feel forgiving. Add a device, no voltage drop. Startup surges don't collapse the bus. Failures are easier to localize. But this comfort disappears the moment power and data share copper. Bus-powered segments, every device is a load. This is where most Fieldbus networks live. In bus-powered segments, devices draw operating power from the bus. Power and data share the same pair. Every device adds electrical load. Foundation Fieldbus H1 and many DeviceNet segments fall here. Now, segment design becomes an electrical budgeting exercise. You must account for steady-state current, startup current, voltage drop along the trunk, spur resistance, power supply headroom. Here's the key shift in thinking. Open quote, "Device count is not limited by protocol. It is limited by voltage at the farthest device." Close quote. You can stay within every standard limit and still fail, silently. The trap. It works until everything starts. One of the most expensive commissioning failures looks like this. Segment communicates fine, devices appear healthy, diagnostics look clean. Then, power cycle, restart after outage, plant-wide startup, and suddenly, devices drop off, communication collapses, faults appear randomly. Why? Because startup current exceeds segment capability. Segment design that ignores startup behavior is incomplete design. Intrinsic safety, IS segments. Power becomes the primary constraint. Now we enter the most unforgiving domain. In intrinsically safe segments, power is not just limited, it is intentionally restricted to prevent ignition. That changes everything. IS segments impose strict current limits, strict voltage limits, strict cable parameters, certified device combinations. The tutorial makes this reality clear. IS Fieldbus segments support far fewer devices due to energy limitations imposed for safety and is no longer engineering preference. It is safety law. IS segment reality, numbers that shock first-timers. Compared to non-IS segments, device count drops dramatically, spur lengths shrink, power margins vanish, expansion becomes painful. This is not poor design. This is physics plus safety compliance. In IS systems, every milliamp matters, every meter of cable matters, every additional device is a negotiation with reality. Designing IS segments like non-IS ones is the fastest way to rework. Comparing the three, the mental table you should carry. Think of segment types like this. Powered segment, communication focused, power is external, device count is flexible. Bus-powered segment, power plus data coupled, device count limited by voltage drop. Startup current matters. IS segment, safety-driven power limitation. Device count sharply restricted. Expansion is expensive. Each step adds constraint. Not because standards want to hurt you, but because energy becomes risk. Why segment design is a project-level decision. Segment design is not a drafting task. It affects cabinet count, power supplies, junction boxes, hazardous area classification, commissioning time, future expansion. Once steel is cut and cables are pulled, segment decisions become very expensive to change. That's why experienced engineers obsess over this phase. Quietly, early, and relentlessly. #, the one sentence that prevents pain. Here's the line I want you to remember when designing any field network. Segment limits are defined by power reality, not protocol capability. If you design with that truth up front, commissioning is calm, startups are boring, the good kind, maintenance becomes predictable. Ignore it and the project will eventually bleed, usually at the worst possible moment. Now that you understand how segment type dictates device limits, the next unavoidable question is, how do we design segments that are not just safe, but maintainable over 10 to 20 years of plant life? That's where installation discipline and maintenance philosophy take center stage. Loop-based segmentation, the design insight that saves projects. This episode is one of those lessons you usually learn after a painful shutdown. It doesn't come from standards. It doesn't come from vendor manuals. It comes from watching real plants fail and noticing why. Here's the core insight, stated plainly. Open quote, segments should be grouped by process loop, not by physical location. Close quote. Once you internalize that, your designs get calmer, your failures get smaller, and your projects stop bleeding in unpredictable ways. The default instinct, group by location. Most projects start with a very human instinct. These instruments are near each other. Let's put them on the same junction box, one segment per area. It feels efficient, it feels neat, it looks good on layout drawings. And electrically, it often works, but operationally, it creates coupled failures. Why location-based segmentation fails under stress? When you group devices purely by location, you unintentionally mix different control loops, different criticalities, different startup behaviors, different failure consequences. Now ask yourself this question, honestly. Open quote. If this segment fails, what stops? Close quote. In location-based segmentation, the answer is usually, open quote, a bit of everything, close quote. That's the problem. A single segment issue can kill multiple loops, affect unrelated operations, create confusing symptoms, multiply downtime impact. Troubleshooting becomes nonlinear. Blame spreads as recovery slows. Loop-based segmentation, a completely different philosophy. Loop-based segmentation flips the thinking. Instead of asking, open quote, where are these devices? Close quote. You ask, open quote, which devices must succeed or fail together? Close quote. A process loop typically includes one primary measurement, AI, one final control element, AO, possibly one or two supporting measurements. These elements are functionally inseparable. If the loop fails, it fails as a unit. If it works as a unit. So the segment should reflect that reality. What changes when you design by loop? When you group devices by loop, one segment equals one control objective, one failure equals one loop affected, one diagnostic trail equals one process story. This creates failure containment. A segment problem becomes local, predictable, easy to isolate, easy to explain. Operations teams love this, even if they don't know why. Startup behavior, where this really pays off. Remember episode 9.1 and startup current? Here's where loop-based design quietly saves you. Different loops have different startup characteristics. Control valves may surge, analyzers may warm up, transmitters may stabilize at different rates. When you mix loops on one segment, startup currents stack unpredictably, voltage dips propagate across unrelated loops, commissioning becomes chaotic. When loops are isolated, startup behavior is contained, power margins are clearer, it only fails on restart, problems disappear. Maintenance reality. Think like the technician at 3 a.m. Now let's leave design offices and go to the plant floor. A technician is troubleshooting a bad reading. With location-based segmentation, they ask, open quote, is it the device, the segment, the power, or something else on the same cable? Close quote. With loop-based segmentation, they ask, open quote, is the loop alive? Close quote. That's a radically simpler diagnostic question. Isolation is faster, confidence is higher. Mean time to repair drops dramatically. Expansion and change, the silent killer of bad segmentation plants, change. Processes evolve, instruments get added. Location-based segments tend to become overloaded, power-starved, impossible to extend cleanly. Loop-based segments scale naturally. Add a loop, add a segment, modify a loop, touch one segment, decommission a loop, remove one segment. Change becomes surgical, not architectural. The cost myth. Isn't this more expensive? On paper, loop-based segmentation can look like more segments, more power supplies, more junction boxes. But in reality, it reduces downtime cost, commissioning time, troubleshooting labor, future rework. Projects don't bleed on CapEx spreadsheets. They bleed during operations and maintenance. Loop-based design pays dividends for decades. The mental model to lock in. Here's the sentence that changes how you design forever. Segments should mirror process responsibility, not physical proximity. Location-based segmentation optimizes drawings. Loop-based segmentation optimizes reality. Once you adopt this mindset, your networks become calmer, more resilient, easier to own. And most importantly, when something goes wrong, it goes wrong small. Now that you understand how segmentation philosophy controls failure scope, the next step is just as critical. How do we install and document these segments so that future engineers don't accidentally undo all this good thinking? That's where installation discipline and maintenance strategy finally take center stage. Field-level control logic, scheduling, failure impact, and why troubleshooting either feels clean or impossible. This episode is where good architecture quietly proves itself, or betrays you. By now, you understand that function blocks can execute in the field and that communication is scheduled, not opportunistic. What most teams underestimate is how deeply those two facts shape control performance, failure behavior, how fast a human can reason through a fault. This isn't theory. This is lived plant reality. Field-level control is not control without a controller. It's control with a clock. When control logic moves into field devices, the system stops being event-driven and becomes time-governed. Every function block executes on a defined schedule, expects inputs at known instance, publishes outputs at known instance. That timing discipline is the difference between a calm, stable loop and a loop that technically works but feels jittery, laggy, or fragile. Control quality here is not about CPU speed. It's about temporal alignment. Scheduling. The invisible backbone of performance. In field-level control, 3 schedules coexist. 1. Block execution schedule, when AI, PID, AO blocks actually run. 2. Communication schedule, when data is compelled, published, and consumed. 3. Supervisory acyclic access windows, when diagnostics, configuration, and maintenance traffic are allowed. If these 3 are aligned, control loops are smooth, latency is bounded, network load is predictable. If they are misaligned, loops become phase-shifted, outputs lag inputs, operators feel instability before alarms ever trigger. This is why scheduling mistakes are so dangerous. They degrade quality without obviously breaking anything. Failure impact. Why field-level control fails differently. Centralized control tends to fail loudly. Controller down, everything stops. Network down, obvious loss of control. Field-level control fails locally and subtly. Because control logic is distributed, devices can continue executing independently. Failure scope depends on where the schedule breaks. That leads to 3 distinct failure patterns. 1. Communication failure. Device alive. Function blocks still execute. Last good values may be held. Control may continue temporarily. This is both a strength and a risk. The process may appear stable until drift accumulates or limits are reached. Good design ensures clear quality status propagation, defined fail behaviors at the AO block, operator visibility into running blind conditions. 2. Scheduling authority failure, LAS timing loss. This is more serious. If scheduling authority is lost, compelled data stops, publisher-subscriber relationships degrade, execution order collapse, and you don't get wrong values, you get wrong timing, and wrong timing destabilizes loops faster than bad data. Well-designed systems have redundant scheduling capability, degrade deterministically, make timing loss visible, not silent. 3. Device failure inside a loop. Here's where loop-based segmentation pays off again. If a transmitter hosting an AI block fails, that loop fails, not the entire, not unrelated logic. Troubleshooting becomes scoped. Open quote, this loop lost its measurement. Why? Close quote. Instead of open quote, something on the network is acting weird. Close quote. Failure containment is the unsung hero of maintainability. Troubleshootability. Why some systems are readable and others aren't. Troubleshooting field-level control is not about packet captures first. It's about mental traceability. In a well-designed system, you can answer these questions quickly. When does this block execute? What data does it expect and when? Who publishes that data? What happens if it doesn't arrive on time? If you can't answer those without opening 5 tools, the system is already too complex. Function blocks help, if you respect their semantics. Function blocks improve troubleshootability only if you treat them as first-class control elements. That means clear ownership of each block, minimal cross-segment dependencies, clean signal flow, AI, PID, AO, no clever shortcuts that hide timing assumptions. When blocks are abused, control paths become non-obvious, scheduling dependencies multiply, small changes ripple unpredictably. That's when engineers start saying, open quote, "It works, but I don't really understand why," close quote. That sentence is a warning sign. Performance is a side effect of clarity. Here's the counterintuitive truth. Field-level control performs best when it is boring. Simple schedules, short data paths, obvious ownership, predictable failure modes. High performance is not achieved by packing more logic into the field. It's achieved by reducing uncertainty in time and responsibility. The mental model to lock in. I want you to remember this framing. Function blocks define behavior. Scheduling defines trust. Failure scope defines maintainability. If scheduling is clean, performance is stable. If failure scope is small, troubleshooting is humane. Field-level control is powerful, but only when you design it to be understandable by the next engineer, not just impressive on paper. That's where projects stop bleeding quietly and start aging gracefully.